So folks, we're going to continue our discussions of linear algebra, and today we're going to look at what are called inverse matrices, and we're going to find methods for certain cases where we can find a matrix inverse. Before we get going, I want to recall the way we use inverse in math so we can be a little bit careful here. So remember that if we're just talking about two numbers, a and here we'll call this a inverse, two real numbers, that we say that a and this number here are multiplicative inverses if when you multiply the two together you get the number 1. Sometimes we're lazy though and we just call them inverses, which is a source of the confusion. These are specifically multiplicative inverses, meaning when you multiply them you get 1. So let's just run through this. Notice that 3 and 1/3 are called multiplicative inverses as their product is the identity, the multiplicative identity 1. If I take 3 times 1/3, I get 1. But to clarify, we would say that 3 and -3 are additive inverses because if I were to add them together, I get the additive inverse, which is 0. So it would be incorrect to just say, what is the inverse of 3? Because I might be asking about the multiplicative inverse, or I might be asking about the additive inverse. This gets more confusing with functions. So for example, the function f of x is the sine of x, and g of x are 1 over the sine of x. These are multiplicative inverses because when you multiply them together, you get the multiplicative identity number 1. That is, if I take sine of x and I multiply it to 1 over the sine of x, I get the number 1. Where sine and minus sine of x are additive inverses, because if I take sine of x and I add to it minus sine of x, I get the additive inverse of 0. Now, usually when we talk about the inverse of a function, though, we're not talking about the multiplicative inverse or the additive inverse. When we talk about the inverse of a function, we're talking about inverses through function composition. If I were to take f composed of k of x, meaning that I take the function f of x and I input the function k of x inside of it, then in this case we would have the sine of the arcsine of x, and we are left with the identity function x, not a 1 here or a 0. We're left with the identity function x. Likewise, if we were to take k composed of f of x, then this would work out as well, that you would have the arcsine of the sine of x, and you would again end up with the identity function x. And I don't know whether I was as careful as I need to be, folks, but there is always an issue with domain and range when you do this function composition. Okay. There's a nice little warning there that I'll let you read through. So we're dealing with inverses now. When we deal with matrices, we want to talk about that. And let me just say that matrix A here and matrix B are what we call additive inverses of each other. Why? Well, the answer is because if we take matrix A plus matrix B, we end up with the 2 by 2 0 matrix. And you can confirm that. If you add matrix A to matrix B, you get a matrix whose entries, a 2 by 2 matrix, whose entries are all 0. Okay. None of those are the inverses that we want to talk about today. And instead today we want to talk about what it means for two matrices. We'll say two matrices are inverse of each other, and we'll say what we mean by that. So if I have two n by n matrices, so everything I'm talking about for this class only deals with square matrices. Okay? And I is the corresponding n by n identity matrix. Then if when we multiply matrix A to matrix B, we end up with the identity matrix, then we say that B is the right inverse of matrix A. Likewise, if we go ahead and multiply matrix B on the left side of matrix A, and we get the identity, then we would say that B is a left inverse of matrix A. Finally, if both products give us the identity matrix I there, then we will say that B is an inverse of matrix A. And if that's the case, we would write B as this expression here, and we read this expression here as A inverse. Okay? So I want you to confirm that matrix B is an inverse of matrix A. So let's first check by multiplying matrix A times matrix B and seeing what we get. So if we take matrix A here and we multiply it on the right by matrix B, let's see what we get through matrix multiplication. When we do this, we have -1 times 5 and 3 times 2, and if we add those two results, we end up with the entry of 1. Likewise, for the 1, 2 entry, I'll take this row, multiply it by this column, and you can confirm that you get 0, and finishing that out. So at this point, we could say that B is a right inverse of A. Likewise, if I were to take matrix matrix B and multiply it on the right by matrix A, matrix A and multiply it on the right by matrix B, we would have 5, 3, 2, 1 multiplied by -1, 3, 2, -4. And if we do this multiplying here, we again get 1 in this entry. We get 0 in this entry, 0 and 1. So we could say that B is a left inverse of matrix A. And putting these two facts together, we've shown that matrix B is the inverse of matrix A, so that matrix B is that inverse matrix. Okay? So we can clarify this a little bit more. This, I'm just going to go ahead and say, you could show this, it doesn't take too much to show, that if matrix A has an inverse, then what is the inverse of that inverse matrix? We're back to the original matrix again. That is, the inverse of matrix A is matrix A. Okay? So another way to say that is, because of that, we can say that we've shown that B is an inverse of matrix A, but likewise A is an inverse of matrix B. So it's kind of a reciprocal property. One is the inverse of the other. Okay. So the only thing I want to clarify is that up until now I've been saying we would call this matrix here an inverse of matrix A. It turns out that the inverse matrices are unique, and I really could use the phrase the inverse of matrix A. So on this next page, let's go ahead and prove that inverses are unique. So here's my proposition. I want to prove that matrix A can only have one inverse. So let's see how we do that. Let's go ahead and suppose matrix A has two inverses, A1 inverse and A2 inverse, both inverse matrices. So what I'd like to do, and this is kind of a clever little proof, it's in any linear algebra book, but it's kind of maybe, for some of you, maybe one of your first math proofs. Let's go ahead and just start with one of them. And I want to show that this matrix right here, this inverse matrix of matrix A, has to be the same as the other, meaning that although I can give them two different names, they're really just two different names for the exact same matrix. And if that's the case, then inverses are unique, meaning matrix A doesn't have multiple inverses. So let's go ahead and show that. So let's start with what we think of as the first inverse matrix, and I'm going to do a little bit of clever writing. Okay? I'm going to go ahead and say I could write this matrix as itself times the appropriately sized identity matrix. So that's the identity matrix, and it has the same dimensions as all of the matrices we're looking at. Okay? Nothing too crazy there. And then the next clever move involves writing the identity matrix as I can write the identity matrix as matrix A times matrix A2 inverse. Why? Because if matrix A2 inverse is an inverse of matrix A, then its product would be the identity matrix. So I've replaced the identity matrix with the product of A and one of its two inverses. A legal move. The next one is, and we spent some time in class showing this, is we have an associative property for matrix multiplication. So what I've done there is I have regrouped the matrix multiplication, and we know that those two sides, this side and this side, must be equal by the associative law of matrix multiplication. So finally, I can rewrite A1 inverse times matrix A, because A1 is also an inverse of matrix A, that it must give me the identity matrix. But what would I take if I took the identity matrix times A2 inverse? That is just A2 inverse. So look what we've done in our string of calculations. We've shown that the first inverse matrix would have to be identical to the second inverse matrix, meaning matrix inverses are unique. There's no two distinct matrix inverses. All right, that was kind of a tedious intro into matrix inverses that we've looked through. And hopefully your question at this point is, wait, I've learned how to verify that two matrices are inverses of one another, but how on earth, if I give you just one matrix, how on earth would you come up with its inverse? And we're going to see how to do that in the next video. Today's video is anti-sponsored by Microsoft. Microsoft, please stop auto-hiding scroll bars, even after I change the settings so that they won't. Thank you for costing my lunch break as I tried to relook up the settings to again make it so you'd stop hiding my scroll bars. If you'd like to have this message removed, Microsoft, please send me the sum of $20, which is how much I value the lunch break that I missed today looking up your settings again.